In this section, I'd like to talk a little bit about the asteroid belt. And to define the asteroid belt, we're going to need to take a look at this diagram. The asteroid belt really is where the concentration of all those white dots is. That each one of those represents an asteroid. And the asteroid belt falls between Mars and Jupiter. Now, it is true that a few of the asteroids do exist inside the orbit of Mars, but for the most part, they're between Mars and Jupiter. And the big question is, why do we have the asteroid belt? Well, the reason for that is that we have an instability in the asteroid belt created by the gravitational pull of Jupiter and the Sun. As you know, Jupiter is quite large, and the fact that the asteroid belt is close to Jupiter causes a strong, or at least the asteroid belt gets a strong pull from Jupiter, and of course the Sun is so large there's a strong pull from that. So it creates this instability so that rather than a few large objects picking up all of the material that is going around in the asteroid belt, orbiting the Sun, they collide into one another and there's no stability generated, so there's no planet. One would expect a planet to be where the asteroid belt is if there wasn't this instability created by the gravitational pull of Jupiter and the Sun, I should say. So let's talk now about what we're finding in the asteroid belt, because there, if you notice on the diagram, there are some places where we have asteroids outside of that white area. And in particular, the green asteroids, those are a very special kind of asteroid called the Trojans. And as you can see, there's two different types of Trojans. There are the Trojans, which are named after famous heroes of Troy, and they're the Greek Trojans, which are named after famous heroes of Greece. And the Trojans, they exist in what we call Lagrangian points. Now, a Lagrangian point is this area in Jupiter's orbit, where anything that gets in that particular position, and you can see they're on both sides of Jupiter, gets in that position, then it's very stable. And they exist out there for practically forever, orbiting with Jupiter. We have Lagrangian points on Earth where we put satellites, and we can get them in the Lagrangian orbits, and they are very stable. So if we want to, do studies of the Sun or even the Earth, we can put them in Lagrangian orbits, and they won't be disturbed. So if you're wondering why we find the green asteroids there, that's why. And then they're the Hildas. Now, the Hildas are quite unique because they have a resonance time to them of 3 to 2. And what I mean by that is that the Hildas, they will orbit 3 times around the Sun, while Jupiter orbits twice. I won't get into the details about why this is stable, but it's a very stable type of orbital resonance. And so you get the Hildas also in a stable area where they can orbit and not be sucked in to the Sun or thrown out of the solar system by a passing star. Don't get crazed on the idea of passing stars. It's not like they're going to be a few miles away or something. I'm talking about light years away, but they come close enough to put a gentle pull sometimes on these objects and can throw them out of the solar system or into the solar system, depending on which side of the solar system the star object is. Well, let me talk a little bit further on this diagram about these resonance times. These are called the Kirkwood Gaps. And on the x-axis we have the number of asteroids, and this is like a histogram where each one of those histograms that you see there, they're formed by a 0.0005 AU. Now, let me remind you that an AU is the distance between the Sun and the Earth, an AU of 1. So that astronomical unit then of 0.0005 is the amount we use to count how many asteroids are in that area. And you can see that on the far left, Mars has an AU of 1.52. Now, that's a measurement of the semi-major axis, which is on the x-axis. And I'm going to have to refresh your memory, I think, about what a semi-major axis is. Remember that all of these orbits around the sun are elliptical, so they do have a major diameter, if you will, to their orbit, and we of course refer to that as a major axis. And then if we're talking about a semi-major axis, that's half of the diameter, so it's referred to as a semi-major axis, semi being half of the main axis. Now, notice that Mars is at 1.52 AU, Jupiter is on the far right at 5.2 AU. Actually, Mars and Jupiter fall off the grass, so you can see the asteroid belt is between those two planets. And look at what we call these Kirkwood Gaps. They're the areas where we don't find any asteroids, and the Kirkwood Gaps are at 3 to 1, 5 to 2, 7 to 3, and 2 to 1. And this is the resonance. So a 3 to 1 Kirkwood Gap means that the object within that gap orbits the sun 3 times to every 1 time that Jupiter does. And it turns out, and I'm not going to get into the details about why, but it turns out that in these areas they're extremely unstable, and objects get thrown out of these areas because of the gravitational pull on them. And they get moved into either the areas that you see there where, that are dominated by asteroids, or they get thrown out of the asteroid belt, either out into the space or into the inner solar system. So again, these are called Kirkwood Gaps. They're due to the resonance around the sun. Now I'd like to show you a video here of the Chelyabinsk meteorite impact. Please keep in mind that a meteor and a meteorite are actually asteroids coming into the atmosphere of Earth. If it comes in as an object in the sky, we call it a meteor, that is a shooting star. But if it strikes Earth, we end up as a meteorite. And Chelyabinsk was a meteorite that came into planet Earth, and as it came in, it got heated up by the atmosphere. It got heated up by the atmosphere, and it had friction in it. And as a result, it exploded, and it exploded with an immense amount of energy. It came in on February 15th of 2013. It exploded. When you've got something coming in at 19 kilometers per second, it's equal to 12,000 tons of TNT being set off simultaneously. And of course, you're going to get a gigantic shock wave that then hits the surface. It struck the city of Chelyabinsk, and of course there wasn't a window left that wasn't broken hardly in the entire city. And of course people got knocked down by this blast, and some people were injured. Fortunately, I don't think there were any deaths. But because the meteorite broke up, we don't find one place where there's a giant crater. It's another case of where the material was spread out over a large area, and you can see one large chunk actually went into the ice and broke through this lake. Well, we get something like Chelyabinsk coming into the atmosphere about once every 50 years, and this is what happens when an asteroid comes into Earth. You can get these kinds of things, and they're rare. You know, like I say, they only happen once every 50 years or so. And more about us trying to find these objects coming into Earth and scouting for them so that we can give warning to Earth if something happens. Now, we have studied an asteroid by sending a spacecraft to it. The Dawn spacecraft went and visited Vesta, which is shown here. And it turns out that Vesta not only has basaltic lava flows on its surface, but Vesta is a differentiated asteroid. And we've talked about how the planets are differentiated. It's the same thing with the asteroids. The things like Vesta, they differentiate because when Vesta started getting bigger and bigger by bringing in smaller material in the asteroid belt to it, the gravitational energy was converted to heat energy, and we also had a lot of isotopes that aren't around today that were decaying back then because we had them formed in a supernova, and we'll talk more about that when we discuss the solar system formation. So these these decaying isotopes created an additional amount of heat, which completely melted the asteroid. So what you've got once it's melted is you've got iron nickel, which is denser, sinking towards the center of the asteroid, and silica, which is lighter, coming towards the surface. So that's what I mean by differentiation. We think that the iron nickel was probably sinking as a liquid, not a solid, but no one's really sure. Silica, though, and iron sinking, that's due to density differences rather than probably crystallization sequences. But still, I want to emphasize caution there. So we've got this iron nickel core, then we have a surrounding mantle made up of olivines and pyroxenes, just like on Earth. We call that rock a peridotite, and these asteroids have peridotites on them. And then on the surface we have a crust, and this crust is made up of basaltic flows, lava flows, and that's probably due to the partial melting of the mantle that's formed of olivine and pyroxene. We get the same thing happening here on Earth. When we have melting of our mantle, it generates partial melting of our mantle, it generates basaltic material, which we see in Hawaii and Iceland and places like that.